Okay, so this is the SUVAT equations, and these equations will only work for a constant acceleration. Okay, so this is constant acceleration. If the acceleration is gradually changing, it won't work. However, if the acceleration changes from, let's say, 5 meters per second for 3 seconds, then 4 meters per second for another 10 seconds, then what we can do, we can chop that scenario into two parts of the story and look at each one individually. But in general, for these equations, we can only do constant acceleration. So let's why are they called SUVAT equations? Well, because the variables that we're going to be looking at spell the word SUVAT. Need a black pen. And so you've got SUVAT. And all these are lowercase, okay? None of them are capital letters. Now, S is a displacement. Okay, and U is the initial velocity. V is the final velocity. And A is the acceleration. And then T is the time. So we've seen a lot of this before at GCSE. We've actually used some of these equations at GCSE physics, not in GCSE. I don't think so in GCSE maths anyway. I want to also look at how some of these are related to each other from the point of view of A-level maths. But let's just color code some of this first. Let's pause the video and we'll use some color. So let's look at what we can say about these different ones. Well, we know a little bit about acceleration already. We know that acceleration is equal to the change in velocity divided by the change in time. So the change in velocity is just going to be the final velocity minus the initial velocity. And then we're going to divide that by the time. So, and if you rearrange this, you'll get the first of the equations. So what I'm going to do, I'm going to multiply both sides by t. That'll give me AT is equal to V minus U. And then I'm going to add U to both sides. So that will give me the equation that is normally seen. V is equal to U plus AT. So that's our first equation then. Let's look at another equation which we can kind of understand. And so with a couple of them actually, we're going to be using we're going to imagine a graph. So we're going to imagine a displacement against, we'll do a velocity against a velocity time graph. So because it's we're taking scenarios where the acceleration is constant, well, we're going to start at some. All right, let me just label the equation, the axes. So this is time, and this is velocity. And we're going to start at some velocity u, and we're going to accelerate upwards. We're going to increase in speed. So that would mean that this point here on the graph would be, on the axes, would be our initial velocity u. And it's going to go up to that point there, which let's give it a dotted line. I need to move this one here. down to here. Okay, and we can say that the time it takes to do that would be labelled as t, and the velocity that it reaches would be labelled as v. So now one of the other things that we can say, hopefully remember, that the area underneath a velocity time graph is actually equal to the displacement, or we can say the area underneath a speed time graph is equal to the distance. So we can take this this shape we've got and chop it into a rectangle, which would be ut, u times t, and a triangle, which would be half v minus u times t. So therefore the displacement, so let's use the colour here. So the displacement is going to be equal to, I'm just going to not bother with the colour here for now. We'll use the colour when we have the final equation, because there's more to be done with this equation first yet. Like that. Okay. Right, just trying to remember. Oh, yes. So if A is equal to V minus U, then V minus U would be equal to AT, wouldn't it? Yeah. So we've seen the bracket there. We've got V minus U. Well, that could be rewritten as AT. So we'd end up with, and let's just move it around a little bit, because this is how you'll see it written. So we've got, we'll take the second term, I'll write that first. So S is equal to UT, that bit there. And then we're going to add half, and V minus U is AT. We multiply that by T again, that's AT squared. So, in fact, why don't I just take both of that and copy it there, and then we can put a squared symbol. So this is our second equation. These aren't in any particular order, I'm just doing them as I remember them, basically. There's no, I'm not doing them in the official order or anything. Or I may be doing them in the official order, but I'm not aware of it anyway. Now, next thing we're going to look at is how we know that the average, the total distance could be calculated by the average speed. If it was a constant speed, the distance would be equal to this just speed times time, or the displacement would be equal to velocity times time. Because the speed is changing, we could say that the displacement, so S, is equal to the average velocity times time. So that could be rewritten as S is equal to, and what you do here is you take the U, we'll add it to the velocity, the final velocity, which is up here, and then we can put that in a bracket, and then we just divide it by 2. If you add two numbers together and divide by 2, you get the mean, and then we multiply it by t. That's our third equation. What's left? Let me just pause. Okay, so the last two, which I'm just going to state, but I can't quite remember at this stage how they are derived. I'm sure we could work it out if we played around with it, but there's other things I want to do. So that is v squared. Let's use the colour again. So v squared. This one was actually used in GCSE. So v squared is equal to u squared plus 2 times A and S. So this one was used at GCSE. It only got brought into the new specification. It wasn't being taught before that at GCSE. And then 5 is very similar to this one here. In fact, it's so similar, I think I'll just copy it and then edit it. And instead of U, it is V. And instead of plus, it's minus. So those are all the equations. So the extra bit that I wanted to make clear of in terms of the A-level physics aspect is the idea of using differentiation and integration for that matter. I mean, as we see, the area underneath the graph is equal to the distance. That's what integration is. So basically we've got to remember that the acceleration is equal to the rate of change of velocity. And that the velocity, and this is where it's a bit difficult actually, so I'm just going to write the word velocity as opposed to writing v, because v means final velocity here. So velocity in general is the rate of change of displacement. Now, most likely with these kind of things, you're probably going to be using mainly this because of the fact that, I just have a feeling with these questions you're going to be mainly using this. This will come into play once you've learned a bit more about SUVAT equations, when we're trying to find the maximum speed or the point at which it stops, and we're basically going to differentiate in order to do that. But so that's going to be the added thing that will come into A-level maths. So that's a brief introduction of it. The other thing you're going to be doing as well is this is going to link very closely to projectile motion eventually. But for now, we're just going to do some SUVAT equations. So we'll start the video there. We'll have a go at trying to apply some of these equations. Okay.